All right, we'll get started now then. The homework Zoom sessions, I had some trouble over the weekend with my computer. Wasn't able to get those. They'll resume tonight though, so we'll have a homework Zoom. I'm sorry? Yeah. The homework Zooms are in Chapter 18 homework. But we're starting Chapter 13 now, so.
Wait, was it Chapter 18 or Chapter 13?
The Zoom is on Chapter 18. I was going to try to finish up Chapter 18 homework over the weekend, but I wasn't able to.
Oh.
After I finish up the Chapter 18 homework, then we'll start the Chapter 13 homework on the Zoom. I'm sorry? Oh, I'm sorry, not Chapter 18, Chapter 17. No, am I doing Chapter 18? Yeah, I'm doing Chapter 18, okay.
So we're starting Chapter 13.
No, actually, Chapter 18 is the buffers and titrations. And so we've been doing buffers and titrations already.
Yeah, but now it's for Chapter 17.
Chapter 17 was, or was it? I don't know. Now I'm getting confused. Let me take a look.
Chapter 17 was buffers and titrations. Chapter 18 was like KSP.
Oh, KSP, that's right.
And we finished Chapter 18 last Thursday. No, last Wednesday.
Yeah, and then we're starting Chapter 13.
Chapter 13.
Yeah, that's right. KSP and KF, solubility and precipitation.
So we started Chapter 18 last week.
Well, before last week, I think. The week before.
So 2 weeks ago.
Yeah. I haven't finished the homework though, so I'm going to work on that. What we're doing now is thermodynamics part 2. Spontaneous change, entropy, and Gibbs energy. Here what we're looking at is the driving force for chemical reactions. We want to quantitate the driving force for chemical reactions. If something's spontaneous, then there is some driving force. So, for example, in chemical reactions, most reactions, the driving force is minimizing energy. And so we minimize the energy, and we see that in nature in general. So, for example, we want to minimize potential energy. Potential energy in this case would be gravitational potential energy. So this would be at a higher gravitational potential energy, and then it would go to lower gravitational. It would never go up to the ceiling, because that would be going from lower to higher energy. I'm sorry? Oh, writing utensil? Yeah, there's some here. I don't know if these work. Somebody forgot their pens, or I have a pen here, or pencil. Okay, there's some here to use. But in chemical reactions, sometimes it does go up to the ceiling. That is, there are some chemical reactions that are endothermic, and they just happen. There's a driving force. But what is that driving force? Because that's like the pen going up to the ceiling. Why would the pen go up to the ceiling? There must be something else driving it. And what that something else is entropy. And so there are 2 driving forces that we think of in nature. One is to minimize the energy, and the other is to maximize entropy. And sometimes they oppose one another. For example, energy is going up, that is, it's going to the ceiling, but as long as the entropy can compensate for that, then that reaction can happen. Sometimes they go hand in hand, so both the energy goes down and the entropy goes up. And so what is the entropy part of this? So energy we talked about in other chapters, but entropy, this is a measure of disorder. And so we should go from more ordered to less ordered states, and that would be one way. Another way of thinking about entropy is it's based on the constraints. So entropy would be like inversely proportional to the number of constraints. Is that no? Let's see, number of constraints. Yeah. The higher the constraints are, let's say, everything has to be in its proper place. Things can't be scattered about. If there's only one place for everything, then the entropy is low. But if you put anything anywhere, then entropy is high. So these are two ways of thinking about entropy. And so what we need to do is we need to go back and review energy. Did I talk about this already? Energy? All right, so let's go.
Yeah, kind of. The E, U, and H.
Yeah, E, U, and H. So what is the difference between E, U, and H? So let's look at energy first. E is the total energy. Which is equal to the sum of the kinetic energy plus the potential energy. Kinetic energy is the energy of motion, but the potential energy, what is that? This is not gravity, The gravitational potential energy depends on how high up you are, but, in chemistry, we don't really worry too much about gravitational potential energy because it doesn't really change much when you're doing a reaction on the bench top. And so the potential energy that we're interested in is chemical potential energy. Chemical potential energy. And that chemical potential energy is you're going to have stable mixtures and unstable mixtures. So for example, dynamite. If you have a stick of dynamite that has the potential to explode, so that we would call high potential energy. Even though it's kinetic energy, it might be a cold stick of dynamite. If it's a cold stick of dynamite, then its kinetic energy is low because there's not much motion, but potential energy is high because it's if you have a hot stick of dynamite, that's even more dangerous because its kinetic energy is high and its potential energy is high. So that would be even more dangerous. And so chemical potential energy does have a potential to react. And so that's what we think about in terms of this. So what is U?
Internal energy?
Yeah, U is internal energy. And what is internal energy? How does it differ from total energy? No, yeah. This is why thermodynamics is a hard subject. It's a hard subject because normally we don't have to worry about, the definitions of these things. We just use energy. Why do we have so many different energies? And so thermodynamics becomes complicated because most people don't learn concise definition of these terms or what they mean versus H, H is equal to the enthalpy. And so to do an enthalpy calculation, delta H isn't that difficult. You do lots of delta H calculations, but what is the difference between a delta H and a delta U? They're both energies, but what's that difference? And so that's what we need to review here. Now, the internal energy, normally when we think about the energy, we think in terms of this. We think in terms of something called the system and surroundings. And the reason we think in terms of system and surroundings is because of the first law of thermodynamics. If you recall the first law of thermodynamics, most people learned that early. First law of thermodynamics just states that energy can neither be created nor destroyed. And so if there's a change in energy, let's say, energy was lost. Well, what happened to that energy? Was it destroyed? Or energy was gained? If energy was gained, was that created? And so we think about the things in terms of the system and surroundings to help us better understand things in terms of the first law of thermodynamics. And so when we think about the universe consists of two things. The universe consists of the system. The system is whatever thing we're looking at or studying. And what we're looking at or studying can be one, an object, or we try to keep it separate. We don't say and or, because if we mix things up, it gets things more complicated. And so the system is either going to be an object or a reaction or process. So the system might be a hot piece of metal. Well, a hot piece of metal is going to have, kinetic energy versus a cold piece of dynamite. A cold piece of dynamite will have kinetic energy also, but both of those will have potential energy. How we visualize that depends on what we're looking at. And so the universe consists of the system plus the surroundings. That's what's going to make up the universe. Surroundings. And the surroundings will be the rest of the universe. Rest of the universe. So, it turns out when we're looking at the total energy, that's kind of complicated because what is the total energy? Is that the total energy of the universe? If we think about the total energy of the universe is fixed. Energy is neither created nor destroyed. So all the universe of the universe is in the universe. There's no other energy, no more, no less. And so when we're looking at a change in energy, we have to break down the universe into smaller parts. If we break it down into smaller parts, the total energy is not the total energy of the universe, because the total energy of the universe is just a fixed amount of energy, fixed amount of kinetic energy and potential energy. Right? And so typically what we do is we'll look at just the energy of the system, whatever thing we're studying, the energy of the system. And so that's only just a small part of the universe. And if we look at that small part of the universe, then the energy of that small part does not need to be constant. We can either gain or lose energy in terms of that. So the energy of the system is just equal to the internal energy of the system. The internal energy of the system would be thought of as the total energy of it. And so the internal energy of the system is just equal to the kinetic energy of the system plus the potential energy of the system. And so how would we visualize this occurring? There's different ways we can visualize this here. And it depends if the system is a reaction, a process, or an object. Let's say the system's an object, like a hot piece of iron. And so here, the system is an object. And so So let's say my object is 50.0 grams of iron solid, and it's going to be at 200 degrees C. So it's a hot piece of iron, so that means it's, high energy. High energy compared to what? Well, high energy compared to this. It's going to have a higher energy compared to, let's say, 50 grams of iron solid at 25 degrees C. So that would be a room temperature. And so we have a hot object and a cold object here. It's the same object. So the system is an object, a hot piece of iron. If I look at the internal energy here, initial, and this would be the system. So I'm going to stop writing the system here. Well, maybe I'll keep writing the system. But this is the internal energy initial of the system. The internal energy initial of the system is equal to the kinetic energy. Well, the kinetic energy is related to 200 degrees C. In kinetic molecular theory, it's directly proportional. The kinetic energy is directly proportional to the absolute temperature, plus the potential energy. And then if we go to the final energy here, U final, so this would be U initial, and then U final here of the system is going to be a cooler piece of iron, and that's going to equal EK final, this is EK initial, plus the potential energy final, this is the potential energy initial. So if there's a change in energy here, this is going to be delta U. Delta U of the system is going to equal delta EK, that is the final kinetic energy minus the initial kinetic energy, plus delta PE, that is the final potential energy minus the initial potential energy. So when we look at this here, the kinetic energy definitely changed. We went from a hot piece of iron to a much cooler piece of iron. So we're losing energy here. How about the potential energy? Does the potential energy change here? And so we have a block of iron. We still have a block of iron. There's no gravity here. This is not gravitational potential energy. This is chemical potential energy. So 50 grams of iron has the potential to do what? Well, it has the potential to become oxidized, rust. But, that's a chemical reaction. And so if you have iron is a reducing agent that can rust.
It's changed with the temperature, so.
Yeah, but the temperature of those, the kinetic, the reaction is going to go faster, but eventually, because we can speed up reactions by heating them up, but eventually the reaction is going to occur even at lower temperature. And so what we say here is that, the potential energy between a block of iron and a block of iron didn't change. It's zero. And so the only change here is in terms of kinetic energy. And so this is a system. When the system is an object, the only change that can happen is its kinetic energy can change. However, if I melt the iron, let's say, liquid iron versus solid iron, then that would be a process. That would be something different. Because when iron melts, there's a melting point and the temperature doesn't change. So its kinetic energy doesn't change. The only thing that can change is its potential energy. The potential energy is different. But let's not get into melting here. What we're going to do is we'll look at the system as a reaction or process. And so in this case, the system is a reaction by process. Process would be like melting or boiling or whatever. So here, if the system is a reaction process, we could look at something with higher chemical potential energy, like methane plus 2 oxygen. This is going to be at 298 Kelvin and 1 atmosphere. We say that this has high kinetic energy. Not really. I mean, it's at the room temperature. It's not really got high kinetic energy, but it does have high chemical potential energy. It has high chemical potential energy because this is an explosive mixture. You know, if I filled up this room with methane, then you got to worry because if somebody has a match or something, it could explode. It's an explosive mixture because we can form something much more stable. What would we form that's much more stable than methane and oxygen in terms of chemical potential energy?
H2O.
Yeah. Yeah. Okay. CO2 and H2O gas isn't really an explosive mixture, unless maybe a carbonated beverage in a can might be, but it's not really like this, which would be an explosive mixture. Now, what we do here is I said or, not and. Normally when we combust it, if you combust methane, temperature skyrockets. It gets very hot. But what we want to do when the system is a reaction process is we want to start it at one temperature and we want to end at the same temperature. And so what I'm going to do is, this is going to get very hot. I'm going to generate steam, but I'm going to wait for that steam to cool down and the CO2 to cool down back to room temperature. When it cools back down to room temperature, I'm left with H2O liquid. And so this is going to be at 298 Kelvin in 1 atmosphere. The reason we do this is because we don't want to mix up the equations. I mean, we could have it at a different temperature. If we have it at a different temperature, then we have to worry about objects cooling or objects heating, which means extra work and complication. And so what we try to do is we try to keep things simple. And that is, when we look at the internal energy here, it's the same. The internal energy initial is equal to the kinetic energy initial plus the potential energy initial. And this is going to be for the system, because that's all we're looking at in this case. And then the internal energy final is going to equal the kinetic energy final plus the potential energy final. And then there's going to be a change in total energy or change in internal energy. The change in total energy or change in internal energy is going to be delta, the change in kinetic energy plus delta, the change in potential energy here. Okay, so the reason we do reactions or processes starting at one temperature and ending at the same temperature is so we can get rid of this kinetic energy term. If we can get rid of the kinetic energy, that is, if we start at one temperature and end at the same temperature, the kinetic energy is the same. That is, the absolute temperature is directly related or directly proportional to the kinetic energy, average kinetic energy. And so this is only a change in potential energy. Here. That's what we want. We just want to look at this as a change in potential energy. Well, this is an exothermic reaction, say that. And so where did the energy go? And the same thing over here. You know, this is exothermic, that is, the iron lost heat. You know, it cooled down. The iron lost heat, you know, lost kinetic energy, cooled down. Where did the energy go? Well, we know that energy is neither created nor destroyed, so that energy had to go somewhere. Where did that energy go? And so in this case, the system lost kinetic energy. That means the surroundings had to gain that kinetic energy. In other words, you know, some of that motion was transferred to the surroundings, so the surroundings had to warm up, basically. And so delta U, the system, this is the first law of thermodynamics. First law of delta U, the system is equal to minus delta U for the surrounding. Now, this minus doesn't mean exothermic. The minus here just means opposite sign of the system. So that minus means opposite sign, you know, when compared to the system. So if the system's exothermic, then the surroundings must be endothermic. If the system's endothermic, the surroundings must be exothermic. Yeah. And so in this case, you know, there's no change in potential energy, so the surroundings increase their kinetic energy in this case. Normally when we think about the first law of thermodynamics, this is the first law. Delta U, the system is equal to minus delta U, the surroundings. But normally when we think about the first law of thermodynamics, we usually write it like this. Q of the system is equal to minus Q of the surroundings. That is, whatever heat is gained or lost by the surroundings will be lost or gained by the system, vice versa. The same thing here, whatever, in this case, potential energy is lost will be gained by the surroundings. It depends on the surroundings. The surroundings, what are the surroundings made up of, and where does that energy go? It can go into increasing potential energy of the surroundings, or it could go into increasing kinetic energy of the surroundings. Just because the kinetic energy in this case is not zero, that doesn't mean the surroundings need not. In fact, in this case, the surroundings, the kinetic energy can go up. And so one of the things that happens in this particular reaction is once the reaction is over, then the system disappears. So, for example, if I do this reaction, is there any methane or oxygen left? No, they react. And I'm left over with CO2 and water, but that CO2 and water is not considered system. This CO2 and water are considered surroundings because these are just leftover objects. The system is the reaction itself. The reaction itself is going to generate energy, change in chemical potential energy. And that energy is going to go into the surroundings. So that energy is going to go into warming up the CO2, warming up the water, and warming up the air and whatever else is around this. That's where it's going to go. Eventually, we'll let it all cool down so we can figure out, how much potential energy was lost completely in this reaction. All right, so when we do these, we figure out, well, the system and the surroundings, when we look at a delta U is going to be heat, that is, how much heat was transferred from the iron to the surroundings. And it could also be work. In this case, no work happened. But delta U, whatever energy is lost or gained is going to be gained or lost in the form of heat and work. There's a sign convention for this. Look at it over here. The sign convention goes like this. The first law states that Q of the system is equal to minus Q of the surrounding. This is just to keep the opposite sign. And then work of the system is equal to minus work of the surrounding. This is to keep the opposite sign. So it doesn't mean one is exothermic and the other is endothermic. It just means switch the signs. Opposite of system. Now, if the work of the system is less than zero, then what that means is the system did work. System does work. Energy is lost in doing that work. So energy is lost when the system does work. However, if the work of the system is greater than zero, then what happened? If the work of the system is greater than zero, then that means the surroundings must have lost energy and the system gained energy. And so here, surroundings does the work. Energy is gained by the system. Energy is gained by the system. And then we have the Q. If Q of the system is less than 0, then energy is lost to the surroundings. Kinetic energy is lost to the surroundings, or heat. If Q of the system is greater than 0, then energy is gained. And the energy that's gained is going to come from the surroundings. So, the most common type of work that's done, I need some room here because I'm going to come back to this reaction here. But the most common type of work that's done is pressure volume work. So let's look at pressure volume work. Here. PV work. Pressure volume work is like blowing up a balloon. If you blow up a balloon, does that require work or energy to blow up the balloon? Yeah. And the bigger the balloon, the more work. But not only the bigger the balloon, but it also depends on the pressure. So if you blow up a balloon, here, it's going to require some amount of work. But if you were to blow up the same size balloon, let's say underwater, under 9 feet of water, it's going to require more work because you're fighting against the pressure of the water, that is the weight of the water. And so for PV work, the work is just equal to minus P delta V. It's going to be negative here because let's say the balloon, if the balloon is 10 liters, it's a pretty big balloon, and the pressure is 1 atmosphere, how much work was done? Well, let's take a look. So an example would be, we blow up a 10-liter balloon. So 10 liters is equal to delta V, and P is equal to 1 atmosphere. If we're underwater, let's say if we're under, 30 feet of water, there will be 2 atmospheres. And so blowing up a balloon under 2 atmospheres is going to be a lot more work, twice as much work as blowing a balloon at 1 atmosphere. And so the work is just equal to minus P delta V. And that's going to be 1 atmosphere times 10 liters. And so this is going to give me minus 10 liters atmosphere of work. Well, what kind of unit is liters atmosphere? That's a strange unit, but actually that's the unit of work, of energy. And so this is energy. The easiest way to do that is, or to use that, is to convert it to joules. And so we'll look at this conversion factor here. The conversion factor is if we take R in units of joules per mole Kelvin and divide that by R in units of liters atmosphere per mole Kelvin, then we can get the conversion factor. A lot of people have R in units of joules per mole Kelvin memorized, so the conversion factor is 8.3145 joules per mole Kelvin. And then R in liters atmosphere, that would be 0.08206 liters times atmosphere per mole Kelvin. And so that's 5 sig figs on the top, 4 sig figs on the bottom. And so we can figure out the conversion here. 8.3145 divided by 0.08206 gives us 101.322. Joules per mole, per liter atmosphere, actually. Moles Kelvin cancel, so I don't need that anymore. And so that's how many joules I have per liter atmosphere of work I do. And so to blow up a 10-liter balloon at 1 atmosphere pressure is going to cost 101 joules worth of energy. And this is going to be negative because I'm going to have to expend that. In other words, I'm going to have to lose that amount of energy in order to blow up this balloon. So I'm going to just go with 4 sig figs. So we'll just go 101.3 joules per liter atmosphere. And so this is going to equal 1,013 joules. So negative 1,013 joules, which is going to be about 1 kilojoule. And so it's going to cost me 1 kilojoule to blow up this 10-liter balloon, or 100 joules to blow up a 1-liter balloon. It's negative because I'm losing that energy having to blow up the balloon. Now to deflate the balloon, let's say to deflate, you blow up the balloon, and then to deflate it, you just, let's say you squeeze the balloon closed, and you just open it, and it'll deflate. And when the balloon deflates, what's deflating the balloon? Well, you have the atmosphere here, and the atmosphere is just going to compress the balloon and deflate it. Or if you're blowing up the balloon underwater, all that water pressure, all the weight of the water plus the weight of the atmosphere will deflate the balloon. And so, to blow up a 10-liter balloon costs you energy, but when you deflate the balloon, did you have to expend any energy compressing the balloon and squeezing the air out? No, you didn't. And so just blowing up the balloon costs energy. It's going to cost you 1 kilojoule of energy. To deflate it, you just let it go. Don't knot it. But you don't get anything for free, even though it seems free to deflate the balloon. If you blow up the balloon, you're fighting against the surroundings. The surroundings is this blanket of air that we live in, or, pool of water or whatever. You're fighting against the surroundings to blow up the balloon. In other words, you got to create 10 liters of space, additional space to blow up your balloon. And that's going to require energy. However, to deflate the balloon, you don't have to do anything, but the surroundings does. Because if your system took up an additional 10 liters and it took it from the surroundings, then when you deflate that, the surroundings will have to blow up a balloon that's 10 liters big. And so, in other words, if the volume changes, let's say, our delta B here was plus 10 liters, but if our delta B here is minus 10 liters, then we aren't doing any work. In fact, what's doing the work will be the surroundings. And so that's going to play a role in how we do our reaction. How we do our reaction, there are 2 common ways that we do chemical reactions. And the 2 common ways, and it's going to make a difference in terms of energy. The 2 common ways we could do this reaction are under constant pressure or under constant volume. And so here, When we do things under constant pressure, we use Avogadro's law. When we do things under constant volume, we use Dalton's law. So what's the difference between Avogadro's law and Dalton's law? Okay. The difference is how we visualize mixtures. So let's just look at the reactants in this reaction. We have 1 mole of methane and 2 moles of oxygen. If we think in terms of Dalton's, then how do we visualize that? Well, we have a total pressure of 1 atmosphere. If we have a total pressure of 1 atmosphere, then Dalton's law says that the total pressure is made up of the sum of the partial pressures. And so if this is a 1-to-2 mixture, that means this 1 atmosphere consists of a 1/3 atmosphere of methane plus 2/3 atmosphere of oxygen. This 1/3 atmospheres plus 2/3 atmosphere gives us 1 atmosphere. This is Dalton's. And so when we visualize the reactants in this under Dalton's, that's the way we do it. However, if we're visualizing this under Avogadro's, we visualize it differently. That is, under Avogadro's, how many atmospheres of methane do we have? How many atmospheres of oxygen? Well, it turns out that under Avogadro's, we have 1 atmosphere of methane and 1 atmosphere of oxygen. So what's the difference? If the partial pressure of methane is 1 atmosphere, the partial pressure of oxygen is 1 atmosphere, and the total pressure is 1 atmosphere, then what must be the difference? What must be the difference is the volume. That is this. In Dalton's, we have fixed volume. So the volume of methane is equal to the volume of oxygen. And we call that constant volume here. And so in other words, the volume of the methane is equal to the volume of the oxygen, which is equal to the volume of the mixture. What's different here is the pressure. The pressure of methane plus the pressure of the oxygen is equal to the pressure of the mixture. So the pressures are additive, the volumes stay constant. Over here in Avogadro's, we have a different situation. In Avogadro's, the pressure is constant. And the pressure of the methane is equal to the pressure of the oxygen, which is equal to the pressure of the mixture. What's additive are the volumes here. The volume of the methane plus the volume of the oxygen is equal to the volume of the mixture. And so in Avogadro's, it goes like this. If I have 1 liter of methane, how many liters of oxygen do I have? I'd have 2 liters of oxygen, and they're all at the same pressure. Most chemical reactions are done under conditions of constant pressure. And so if we did this under constant pressure, then it's an open beaker, open container. Whereas if we do reaction under constant volume, we do it in a bomb. And so there are 2 ways we could do this. In the open laboratory, this would be constant pressure. If we did this in a bomb, then it would be constant volume. Those are the ways we can think about it. Well, what are we doing this reaction under? Constant pressure or constant volume, typically? So when I burn this in the open lab, it's under constant pressure. I don't put this into a bomb and burn it inside a steel bomb. It's a steel bomb because what happens is pressure can increase or decrease. We've got to make sure that the container doesn't explode or implode due to pressure changes. And so what's happening in this reaction? Well, let's take a look at what's happening in this reaction. And when we take a look at this, we have to go back to molar volume. You guys remember molar volume of a gas? Okay, let's look at molar volume of gas. molar volume of the gas. A lot of people memorize this in Chem 4, but I don't. It's not really worth memorizing. Many have memorized the molar volume at STP, standard temperature and pressure. Standard temperature is 0 degrees C or 273 Kelvin. Pressure is 1 atmosphere or 1 bar. And they had 22.4 liters per mole. Have you heard of that number? Maybe. And so this means a mole of gas at STP occupies 22.4 liters. This is 1 atmosphere though. At 1 bar, it's a little bit bigger, like 22.6 or something like that. And so this is at 0 degrees C and 1 atmosphere. Okay, so how often do you work at 0 degrees C? Yeah. Actually, probably not often, because if you had to turn the temperature down to 0 degrees C, then it would be very uncomfortable working there. I went to visit a frozen food warehouse once. The temperature was minus 5 degrees C. You know, the outside temperature was over 100. This was in the middle of LA. But the inside temperature was minus 5. And so you see these people dressed in like the Arctic clothing, like they're going to the North Pole or something, or the South Pole, you know, fully dressed in heavy parkas and stuff. And it's over 100 degrees outside, you know, but they're dressed in these parkas because it's so cold in their warehouse, you know. And so how often do we work in freezers? Not often. In fact, very rare. And so this isn't very useful. Not useful. In fact, I memorized this when I was a student and never really used it. What would be a lot more useful would be what? Yeah, at 25 degrees C. And so what would be the molar volume at 25 degrees C in 1 atmosphere? So the molar volume is equal to the volume per mole, which is equal to P equals nRT. So we put V over N, that leaves us with RT over P over here. And so we plug in R, which is 0.08206 liters times atmosphere per mole Kelvin. T we'll plug in at 298.15 Kelvin. P I'm going to put in as exactly 1 atmosphere, etc. And so we should get the molar volume to 4 sig figs. So 0.08206 times 298.15. Okay, it didn't work.
24.5.
Okay. Give me more. We're allowed 4 sig figs.
24.466. So 24.4.
6
Yeah.
liters per mole. All right. So this to 4 sig figs would be 24.47 liters per mole, or about 24.5 liters per mole, or about 25. Depends on how precise we want to be. So if we're just estimating things, then 25 liters per mole is about right. And so a mole of gas at room temperature will occupy about 25 liters. Whereas if we cool that down to freezing, 0 degrees C, then it occupies only about 22 liters. And so the volume expands and contracts with temperature. This is at 1 atmosphere, but standard pressure is either 1 atmosphere or 1 bar. I can convert this into bar here. Let me do that up here. By multiplying. If I take this one and just multiply it by this, there's 1.01325 bar in every 1 atmosphere. And what will that give us as far as molar volume goes? And so if I take this number we just calculated and multiply that by 1.01325, so 24.466 times 1.01325 gives us 24.790. So that gives us 24.790 liters per mole, which is going to give us to 4 sig figs, is 24.79 liters per mole, or about 25 liters per mole. So if we aren't very precise, then it's roughly 25 liters per mole. But this is going to be at 1 bar of pressure and the same temperature. And so 1 bar and 298 Kelvin. And so bar is a little bit lower pressure, so the gas can expand a little bit. So it's a little bit bigger. Rather than 24 and a half, it's like 24.8. So it expands about 300 milliliters due to the lower pressure, same temperature. So anyway, let's go back to this reaction here. And this is our system. Our system is a reaction. Our system is this combustion of methane. And after the combustion's over, then everything else that's left over is the surroundings. And so when we look at the system here, we have to look at how the system interacts with the surroundings, For example, when I blow up the balloon, I'm fighting against the surroundings because I need to take 10 liters away from the surroundings, so it's going to work. Whereas when I'm deflating a balloon, then I don't have to do anything because the surroundings will do that work. And so if I'm at 298 Kelvin in 1 atmosphere, then a mole of methane is going to occupy about 25 liters. 2 moles of oxygen will occupy about 50 liters. And if I add these up, and I don't want the pressure to change, so if I take 25 liters of methane plus 50 liters of oxygen, I'm not going to compress it into a smaller volume. I'm just going to add them up, and I don't want higher pressure, and I don't want lower pressure. I just want the same pressure. And so to add these up at the same pressure, then that means the total volume of this will be 25 plus 50 is going to give us 75 liters. And so I'm going to have 75 liters of mixture. In that 75 liters of mixture, I'm going to have 1 atmosphere of methane, which is going to occupy 25 liters. And I'm going to have 2 times that, which will be 50 liters, but it's going to be the exact same pressure, 1 atmosphere. So that's how it works. And so altogether, I have 75 liters initial. So this is my V initial. V initial is about 75 liters. What is V final here? Well, it looks like the same amount because I'm going to have about 25 liters of CO2. But this is not gas. If this were H2O gas, it'd be 50 liters. But that gas, which is mostly empty space, will now be liquid, which is mostly not empty space. And so 2 moles of liquid water weighs, 18 grams per mole. This would be 36 grams. 36 grams of liquid water would be the same as 36 milliliters because the density of water is about 1 gram per milliliter. And so the V final is going to be 25, and then 36 milliliters is 0.036 liters. And so it'd be 25 liters from the CO2 and 0.036 liters from the liquid water. And so it's about 25 liters. About 25 liters. So being a liquid, the volume is so small compared to a gas. Gas, the volume's 1,000 times bigger for a given amount. And so what was delta V here? If we look at delta V, what happened to the volume? Yeah, delta V is negative 50 liters in that case. Well, we lost 50 liters of volume. Well, that's like deflating the balloon. If we deflate the balloon, we don't really have to do any work. Right? And so if I had a 50-liter balloon and I just poked a hole in it and just let it deflate, I don't have to do any work. Or just let it deflate naturally. But it's not free because somebody had to do the work to deflate the balloon. Who had to do the work to deflate the balloon? The surroundings. And so what this means is this. This means that I'm going to get a different amount of energy depending if I do this reaction under constant pressure conditions versus constant volume conditions. Because in constant volume, like if I did this in a bomb, the volume can't change. And so even though we lost some gas here and the volume wants to contract, it can't. Because it's in a bomb and this bomb can't implode. And so the pressure will change, but the volume won't. And so if I do this under constant volume, then delta V is equal to 0. Delta V is equal to 0, then nobody's doing any work. And I'm going to get the change in internal energy here. But if I do this under constant pressure, then, work is going to be done by somebody if there's a change in volume. And we have to factor that in. In this case, the surroundings does work. If the surroundings does work, you know what happens? I get a little bit of extra energy. And so if I'm heating up some coffee or heating up a pot of water, if I heat it up doing it under constant volume, I'm going to get less energy than if I heat up that pot of water doing it under constant pressure conditions. And how much is the difference in energy? Well, that's going to be, if that's my delta V, then work is equal to, we can calculate the work. Work is equal to minus P delta V. Okay, the pressure is 1 atmosphere, and then delta V is going to be minus 50 liters. And so this is going to be plus 50 liters atmosphere. And then I multiply this by 101.3 joules per liter atmosphere. And I can figure out how many joules of work this is going to take for the surroundings. And so
5,065.
5,065 joules. And this is going to be about 5 kilojoules, let's say. And so in other words, the surroundings, it's weird, energy is neither created nor destroyed. So the surroundings is going to have to use 5 kilojoules of work to increase its volume. So the volume of the system decreases, the volume of the surroundings increase. That 5 kilojoules goes somewhere, and that 5 kilojoules goes to the system. And so in this case, I get 5 kilojoules more per mole burning this under constant pressure than I do under constant volume. It's kind of weird, but that's the way. And so whenever we do chemical reaction, we have to think about this. We have to think, are we doing this reaction under constant pressure or under constant volume conditions? And then figure things out. And so to make life easier, most of the reactions we do are constant volume in a bomb or constant pressure in the open lab. Most of the chemical reactions we do are under conditions of constant pressure Well, constant pressure is, yeah. And so that brings us to this. What are the different energies? The different energies here is if you do constant volume, then use delta U, the change in internal energy. Q plus W. If we do this under constant pressure, then use delta H. Now, what's the difference between U and H? And delta U and delta H? So let's talk about that now. U is equal to the internal energy, which is just the total energy of the system. This is the system. Of the system, total energy of the system. What is H? H is of the system is equal to U of the system. But there's one extra thing. And the one extra thing is the pressure volume state for the system. PV state. Of the system. Because what we're dealing with here is PV work is unavoidable at constant pressure. At constant pressure, in order to maintain that constant pressure, the volume has to be able to expand or contract. It has to be able to expand if we add gas. It has to be able to contract if we remove gas. And so when we do a reaction at constant pressure, PV work is mandatory if there's a change in moles of gas. And so it's unavoidable. And so in order to figure out what that change in energy is going to be, we have to look at how the system interacts with the surroundings. And that's what H does. H just, if we don't care what's happening with the surroundings not going to bother us. We're not going to bother the surroundings. The only thing is we're going to just exchange. I haven't talked about this, but we're going to exchange that. Then this is all we worry about. But if there's going to be any kind of change in the volume and we're doing it under constant pressure, then we got to do this. And so H is the energy with the PV state in there. And the PV is also energy as well, but energy, well, we have to add this. It has to be done under constant pressure and only PV work. Pressure volume work, that is blowing up a balloon and doing it. Okay. And so what we end up with is something like this. Delta U is the change in the internal energy. The delta H is the change in the internal energy plus, whatever little bonus in energy we get over here. And so delta H is equal to delta U plus P delta V, depending on the change between the final and the initial. So this P delta V could be a little bonus. Like in this last reaction, we got a little bonus of 5 kilojoules. And so that would be like, you get a little bonus, like a gas bonus, from the governor. Let's say he's going to give you a $200 gas bonus, and then you can use that. Well, we just got a 5 kilojoule energy bonus from the surroundings. Or let's say the opposite thing happened. That is, let's say the volume had to expand. Let's say we went from 75 liters to 150 liters. Then the system's going to have to lose energy. The system's going to have to expend energy to increase its volume. So it could be a tax. And so it's either a bonus or a tax. And so one way we think about this is delta H is your net income. your take home. Delta U is your gross income. And you could either have a bonus on that or tax, so that your net could be higher or lower, or there could be no difference. That is, let's say it's tax free. That is, nobody would do any work. Let's say we started off with 75 liters and we end up with 75 liters. So nobody's doing any work for that reaction anyway. So that would be it. And so for us, it would be much more useful to understand things in terms of delta H rather than delta U, because we don't know what's happening with delta U in terms of what's going on with the surrounding and the volume and the P delta V work. And so delta H is kind of like the net energy change after factoring out the PV work that needs to be taken care of. So typically when we want to minimize energy, we're thinking about minimizing enthalpy or minimizing internal energy, those things. Minimizing, so exothermic is good in minimizing energy. Endothermic isn't so good. We look at that. What's going to be most useful for us, depending on the conditions we do, will be delta H. But sometimes we do things under constant volume conditions, so we'll be interested in delta U. We'll have to be able to relate things. So for example, sometimes when we do a combustion calorimetry like this, doing combustion calorimetry in the open lab is more difficult than doing combustion calorimetry in a bomb. And so if I wanted to measure the delta H of this reaction, I'd probably do this in a bomb. If I did this in a bomb, am I getting delta H or am I getting delta U? Did I say? Did I write that up here? And so if we do things under constant volume, we use delta U. If we do things under constant pressure, we use delta H. So if I'm measuring how much heat I'm getting from this combustion reaction, most likely I'll do this in a bomb. But if I did this in a bomb, I'm not letting the surroundings interact with the system. The surroundings will be isolated from the system. So if I want delta H, I'm not getting delta H from a bomb. What I'm getting from a bomb calorimeter is delta U. So if I get delta U, then what I'm going to have to do is I'm going to have to do an extra calculation to figure out what delta H is. So if I know what the delta U for this reaction is, then I'm going to have to do an extra calculation, which is this, just to figure out if I did this under constant pressure, what would the volume have changed? And then calculate how much work is involved in that volume change, and then correct it. And so, well, calorimetry is kind of a pain. So if we're into, and now we're going to focus on delta H, since practically all our reactions are going to be at constant pressure. And so what are the ways of determining delta H? One is calorimetry. And when we do calorimetry, it's like coffee cup calorimetry. Coffee cup calorimetry is not a bomb, it's not constant pressure. Coffee cup calorimetry will give us delta H. We can't burn methane in coffee cups, it doesn't work very well. And so, calorimetry, either we can use, but with delta U, it's a little bit more work. But that's not the easy. Calorimetry is a lot of work, and so there are easier ways to do it. In other words, we can calculate what our delta H is using Hess's law. Or delta H is a formation. That is, delta H of reaction is equal to the sum of the delta H's of formation of the products minus the sum of the delta H's of formation of the reactants. Do you remember doing these type of calculations? Products minus the reactants, etc. And so we can figure out what's going on with the energy part of the driving force, but we also need to figure out what's going on with the entropy part of the driving force. And so let's talk about entropy. Next. Entropy is given the symbol S. S is called the absolute entropy. And what we do with entropy is we figure out delta S. Delta S is a simple calculation. It's the entropy of the products, the sum of the products minus the sum of the reactants. Entropy of the reactant. There's a big difference here, though. And in other words, this is equal to S final minus S initial. These are called absolute entropies. No, we don't calculate delta H and delta U using absolute entropies. So let me just do this as an aside here. Delta H would be H final minus H initial, but we don't do this calculation. We don't do this calculation because it's very difficult to determine absolute enthalpies. There's too much error associated with it. And so we use other means to figure out what delta H is. You know. Delta U is also U final minus U initial. And for the same reason, it's too hard to figure out the absolute energies. So we use other means. And so what are the other means? For delta U, the other means are delta U is equal to Q plus W. So we can figure out Q is the heat, W is the work. There's different kinds of work too. There's not just PV work. There's electrical work, mechanical work, etc. Or delta H, delta H, if we have delta H equal to Q, then it's equal to delta U minus W. That's one way, etc. There are lots of ways. But here we're going to use absolute entropies. And so the first thing is, how do we determine what the absolute entropies of things are? We can determine the absolute entropies with the aid of the third law of thermodynamics. Third law. I'm skipping over the second law for right now. The third law of thermodynamics states that the entropy of a perfect crystal, the entropy of a perfect crystal at 0 Kelvin is 0. And so that tells us what 0 entropy is. 0 entropy is a perfect crystal. In a perfect crystal, there's only one arrangement of the atoms. And it's at 0 Kelvin. If we increase the temperature, then the atoms start to vibrate. As the atoms start to vibrate, there are different positions that they can be in three-dimensional space. And that's going to increase the entropy. So this can be seen probably easiest if you look at the entropy in terms of constraints. That is, if we look at entropy in a number of ways we can arrange things. So here, this is maximally constrained. It has to be perfect. So everything has to be in its correct position. So this is the highest number of constraints you can have. Because you aren't allowed to have any variations of that. take a look here at the Boltzmann's view of entropy. Boltzmann's view of entropy goes like this. I'm going to jump ahead to the Boltzmann equation. I just passed. Here's Boltzmann, but this is the Boltzmann equation. The Boltzmann equation is engraved above his headstone there. And that is the absolute entropy is equal to KB, which is the Boltzmann constant, times the natural log of W. W is the number of ways to arrange things. If there's only one way of arranging things, then you can't get more constrained than that. And there's only one way of arranging things here in a perfect crystal at 0 Kelvin. Perfect crystal means there's no defects, that sort of stuff. And so, since there's only one way of arranging all the atoms in perfect crystal, then W is equal to 1. We call it a 1 microstate. There's only one microstate. And the natural log of 1 is 0. And so the entropy is equal to 0. And so that would be it. But all of a sudden, when you introduce more ways of arranging things, then the entropy is going to go up. And so one way of figuring out what the entropy is just to calculate the number of ways of arranging things. The number of ways of arranging things, each way is called a microstate. So it's the number of microstates for a given system. And so if we have 5 objects, and these are the energies, how many different ways can we arrange it? Well, here there's one way, here there's 5 ways of arranging it over here. We can calculate the entropy depending on how many ways we can arrange certain things. There's 6 ways. And so we can enumerate the number of microstates. That is just counted up. This is called statistical thermodynamics. And you just add it up, the ways, and then you calculate the entropy. Well, the problem with doing this statistically like this is when we're dealing with just even 1 gram of substance, 1 gram of substance has so many atoms, you can't even count it. If you had 1 mole of substance, it'd be even more atoms. And so the numbers are going to get huge, and to count the individual microstates is going to be very difficult. That's why they use statistics to do it, so you aren't counting individual microstates, which would be way too much to count. So, for example, if we had 10 to the 23rd, like a mole of microstates, then what would that look like? Well, the number of ways of arranging, let's say if we had 10 to the 23rd atoms, the number of ways of arranging those is much more than 10 to the 23rd. It'd be 10 to the 23rd different ways of arranging that, which would give you some number like this. And then we would plug that in. And so this would be statistical physics or statistical mechanics, because how can you count that number? You can't. How can you draw that many? You aren't going to be able to do it. You got to do it statistically. And so this is one way of doing it. And so to determine the entropy, there are 2 ways that we can do it. Okay. We're out of time, so we'll talk about it next time. But one is this calculation, theoretical calculation like this, and the other is experimental. So we'll talk about that next time. Tomorrow we're going into the computer lab again, so work on the lab reports tomorrow. Thanks, you too. You too.